This question, it's sort of like one we've done in electric field and electric potential before. What if we had two current carrying wires? Where would the magnetic field be zero? So where on the vertical line where the net magnetic field be zero? So we know that current carrying wires make magnetic fields. We know that the net field is those two added up. What we're asking now is the net field, which is the field due to wire 1. Let's say this is current I1 and this is current I2, plus the field from wire 2. Where is that equal to 0? If those two vectors are gonna sum to be 0, it means that B1 and B2 are equal and opposite. Let's deal with the opposite bit first. What does it mean that those vectors are opposite? So first I'm just going to draw a straight line along this axis because our answer is going to be somewhere on this axis. Let's think, just like we did when we did this as an electric field vector, I have three choices for my answer. Maybe it's up here, maybe it's in between, and maybe it's down here. So let's think about the field in each of those three places. So up at the top, somewhere up here, for the moment, pretend you don't see this big blue circle and this red circle. I put that there to cheat for me in drawing my fields later on. So somewhere above wire I1, the magnetic field would make a big circle around I1. The direction of the magnetic field right here due to wire 1 would point this way. So my thumb goes into the page, the magnetic field B1 would point this way. At this point, I'm pretty close to this big wire because this is 250 milliamps. And since I'm close to this wire with a big current, I think it's going to be a big field. What about my magnetic field at this point due to wire 2? So wire 2 has a smaller current, that's 125 milliamps. My magnetic field at this point due to this wire, my current is out of the page. I ask, what are my fingers doing up here? They're pointing to the left. So my magnetic field will point to the left. At this point, I'm really far away from this small current. I'm going to get a small field here, B2. So these two vectors, they are opposite, but they're not equal. So our net field here cannot be equal to 0 because these two vectors cannot have the same size because we're always too close to the big current. Okay, what about somewhere in between? Somewhere in between now, let's say right about here, our magnetic field due to wire 1, so our thumb goes into the page, we see that our knuckles are pointing to the left. Our magnetic field due to wire 1 points to the left. So there's our B1. What about our magnetic field due to wire 2? Our thumb comes out of the page, my fingers are pointing to the left, my magnetic field B2 is to the left. So maybe here they could be equal, but they're not opposite. So that gives us one choice. It must be down below wire 2. So I'm going to draw a dot here. The directions of my fields down here, so my magnetic field around wire 2 is a big circle that I'll have cut through my point. The orientation of the circle comes around this way. The direction of my field down here, I put my thumb into the page, I see that my fingers are pointing to the left. B2 points to the left. There is B2. I'm kind of far away from that big current, so I kind of get a medium-sized magnetic field. All right, what about the magnetic field due to wire 2? That current comes out of the page. It makes big circles around the wire, coming around this way. The direction of the field right here, I put my thumb out of the page, my knuckles on top of my point, my fingers point to the right. That B1, oops, sorry, I labeled that B2, should have been B1 because it was due to the upper wire. This one is due to the lower wire, that one points to the right. Here, I'm pretty close to a big current, so I get kind of a medium magnetic field, B2. So it's down here where they can be equal and opposite. So down here is my winner. This is the position I'm trying to find. I've now dealt with the opposite. Next, let's deal with the equal. To deal with the equal bit, I know that the magnitude of B1 is going to be equal to the magnitude of B2. The magnitude of B1 is mu naught I1 over 2 pi R1. equals the magnitude of B2 mu naught I2 over 2 pi R2. Let's get R1 and R2 in our picture. R1 is the distance between wire 1 and our point. So this is R1. R2 is our distance between wire 2 and our point. This is R2. We know that the distance between the two wires is 10 centimeters, so we might notice here that R2 plus 10 centimeters equals R1. There's a relationship between our two distances. And I'm looking at my equation. I've got mu naught on both sides, 2 pi on both sides. That simplifies a little bit. I'll do a little cross multiplying. I1 times R2 equals I2 times R1, but R1 is R2 plus 10 centimeters equals I2 R2 plus I2 times 10 centimeters. Okay, we can solve this equation. So then we're trying to solve, so I1 R2 minus I2 R2, just trying to make sure I don't get any of my symbols goofed here, equals I2 times 10 centimeters. R2 is I2 divided by I1 minus I2 times 10 centimeters. Yeah, I think I got all my signs fine here. I2 is the lower current, 125 milliamps, divided by I1, 250 milliamps. Subtract I2, 125 milliamps, times 10 centimeters. Put all that through the calculator, and what we get is 10 centimeters. So R2 is from wire 2 to our point. So we say that B equals 0 at 10 centimeters below wire 2. So we found where the net magnetic field is 0. Let's go through and let's start another homework problem. So our next homework problem is also going to be a bit of a combination. Current carrying wires, a couple of them, and their feeling forces. So in this example, we've got our long straight wire. That's on the top. It's carrying a current of 14 amps. Next to the wire is a square loop. Each side has a length of 1 meter. The loop carries a current of 2.5 amps. Find the net force acting on the loop. Okay, so if we're trying to think about what's happening here, is that our top wire, and why don't we say that that current is I1? So our top long straight wire, I1, is carrying a current, therefore it makes a magnetic field. This loop sits in that magnetic field. Why don't we identify the direction of that magnetic field? So rather than twist my hand, I'm going to twist my paper. So my current is this way. My magnetic field everywhere on this side of the wire is going to point into the page because I see that my knuckles are going into the page. So this wire creates a magnetic field, that's big circles around the wire, and over here that magnetic field points into the page. So I'm going to draw that. So B points into the page. We know how to calculate B. It's mu naught times I1 divided by 2 pi r. So we're going to have to do that calculation at some point. Okay, so there's the B made by wire 1. So I1 makes, why don't we even get a couple of notes down here? So I1 makes magnetic field B. Loop with current I2. So we'll say the 2.5 amps is I2. Loop sits in B. We know that current carrying wires feel magnetic forces. Therefore, loop feels magnetic forces. Okay, hopefully the idea is clear. Our loop has 4 long straight edges. Let's calculate the force on each of the 4 edges, then we'll add them up to get the net force, and we'll have one little shortcut in the middle. So let's deal with the top loop first. I'm going to call that top loop just side A. Could probably give it lots of different names. So this top one is going to be side A. What's happening on side A? So I'll just put a little a here. So what happens on side A? We know that this length of wire on side A is sitting in a magnetic field created by wire 1. Let's find that magnetic field. B1 equals mu naught times I1, the current carrying wire making the magnetic field, divided by 2 pi times R1. R1 is my distance between my wire and the place where I'm trying to find the magnetic field. So that's R1 for part A, equals mu naught 4 pi times 10 to the minus 7 Tesla meters over amps times current I1, 14 amps, divided by 2 times pi. This R1, see that this length is 1 meter, this length is 1.2, R1A is 1.2 minus 1, or 0.2 meters. So this magnetic field B1 equals 1.40 times 10 to the minus 5 Teslas. We can call that minus k hat, or into the page. Okay, next, there is a current going through length A. It's a current carrying wire sitting in a magnetic field, so it feels the magnetic force. Let's find the direction of that magnetic force with the right-hand rule. Current is this way, field is into the page, force points straight up. So your thumb is your current, your index finger is your B, your extended middle finger is your force. So the direction of the magnetic force on side A points straight up. The magnitude of my force on side A is the current inside A, that's I2, times the length of side A, times the current times the magnetic field it's sitting in, B1A, times the sine of the angle between the length and the magnetic field, that's equal to 90 degrees. Okay, I2 is 2.5 amps, LA is 1 meter because it's the length of the edge of a square, B1A we just found. That gives us the magnitude of the force, 3.50 times 10 to the minus 5 newtons. The direction of the force is straight up. We'll call that the positive y direction. So there's the force on side A. Next, what about sides B and C? So let's deal with those two together. So side B is right here. The current is flowing down, the magnetic field is into the page. So current is down, field is in, force is to the left. So you can do this along with me. I know it's hard to show my hand on the iPad. So the force is to the left. So here is the force on side B. So this is side B. On side C, color inside C here, current is up, magnetic field is into the page, force is to the left. That force is to the right, this force is to the left. There's the force on side C. Look at the symmetry between B and C. They're the same length, they're in the same field. The only difference is that here the current is down, here the current is up. The forces are in opposite directions, and they're going to have the same magnitude because they have the same B, the same length, the same I. So sides B and C, they have symmetry. Therefore, FB plus FC equals 0. Okay, so we don't have to do quite as much work with that one. Last side is our bottom one. Let's call that side D. Grab the purple pen for that one. So here's our side D. Let's ask what's happening here. Side D. So side D sits in a magnetic field made by wire 1. Let's figure that out. Side D. B made by wire 1 at side D equals mu naught times I1 divided by 2 times pi times R from wire 1 to side D. R to side D is from here to here, R1D. That's 1.2 meters. 4 pi times 10 to the minus 7 Tesla meters over amps times I1, because I1 is the current making the magnetic field, divided by 2 times pi times 1.20 meters, gives us a magnetic field B1 at side D is 0.233 times 10 to the minus 5 Teslas into the page. Okay, so that's the magnetic field that side D is sitting in. Because it's a current carrying wire in a magnetic field, it's going to feel a magnetic force. Let's get the direction. Current is to the left, magnetic field's into the page. The magnetic force points down. So the magnetic force on side D points straight down, FD. To find that magnetic force, we can find the magnitude. FD is current flowing through side D, that's I2, times the length of side D, times the magnetic field it's sitting in, times the sine of the angle between L and B, that's 90 degrees, 2.5 amps times 1 meter, that's the length of the side, times B, 0.233 times 10 to the minus 5 Teslas. So the force on side D is, put that through the calculator, 5.83 times 10 to the minus 6 newtons is minus 5.83 times 10 to the minus 6 newtons J hat, minus J hat because it points down. Things to notice here. B1 here is smaller than B1 here. That makes sense. This bit is further away and the magnetic field is smaller as we get further away. Because the field is smaller, the force has a smaller magnitude. To get our net force, we have to add them all up. So our net force F is equal to the force on A plus the force on B plus the force on C plus the force on D equals this plus this plus this equals 2.92 times 10 to the minus 5 Teslas J hat. So that's the net force on the loop. Before we leave this example and move on to some other things, I am going to point out something that's kind of interesting. So you see this wire has a current that flows to the right, this wire has a current that flows to the right, and this wire is attracted to it. So the force on this bottom wire is towards the top wire. Turns out that any wires with current flowing in the same direction, those are going to be attracted. With the bottom one, the top current here in this top wire, that flows to the right. Our current here flows to the left, and we see that this force is away. Any two parallel current carrying wires, when the currents are in the opposite directions, those are actually repelled. That's sort of an interesting observation.